Hello dear, welcome to our YouTube class. Today we are discussing EMF and internal resistance. So suppose we have a battery and the battery does have some internal resistance inside it. Now if the battery is connected with the voltmeter, then whatever voltmeter reading we get, this is going to be the EMF of this battery, electromotive force of this battery, when just a voltmeter is connected with the battery, because in this connection the battery is said to be open. That means it is an open circuit. The battery is not connected with any other components, so it is not a closed circuit, and in an open circuit current does not flow. And this is why whatever the voltmeter reading we get is what we consider as the EMF of the battery. So in this example, we have considered this battery voltage, means EMF, is 6 volt, because in an open circuit we got the voltmeter reading to be 6 volt. And I drew the equivalent circuit diagram as well. Just the battery along with the internal resistance is considered to be inside a box, and we have connected the voltmeter across the two terminals of a battery. But it is not a closed circuit, because ideally the voltmeter has infinite resistance, so current flowing through the voltmeter is effectively zero. So we get the voltmeter reading in this open circuit as the EMF of the battery itself. And now we are going to make the connection in such a way that battery is connected with the bulb, and we have connected a voltmeter across the bulb. Now if I connect the voltmeter across the bulb, or if I connect the voltmeter across the two terminals of the battery, means the same. It is the same connection. I do connect the voltmeter across the two terminals of the battery, or I connect the voltmeter across the two ends of a bulb, it gives me the same reading. So here the voltmeter reading I observe, and it is not going to be 6 volt the way we have seen earlier. The same battery, we have connected a bulb across it, but we see the voltmeter reading to be something less than 6. It is a closed circuit, and current flowing through the closed circuit is not zero. Some current flows through the bulb. Since the battery does have some internal resistance, and due to that internal resistance, some voltage is lost inside the battery. So outside the battery, we have less than its EMF voltage or EMF value. So I again drew the equivalent circuit of this diagram, as I said, that the bulb is connected with this battery that has internal resistance. We connect the voltmeter across the bulb, or we connect the voltmeter across the two terminals of the battery, gives me the same reading, because in this particular circuit there is no other external resistor except the bulb. So I connect the voltmeter across the bulb, or I connect the voltmeter across the two ends of the battery, gives me the same reading, and here the voltmeter reading is not equal to the EMF, what we found in an open circuit. All right. So current flows here, and this current is flowing through the internal resistance as well. If the current flows through the internal resistance, some PD is dropped inside the battery. And that's why outside the battery, the voltage is less than the EMF of the battery. All right. So here we try to get acquainted with the terminologies. In this way, when the connection is made, the voltmeter reading is considered to be as the terminal PD, V subscript T, terminal PD. And the EMF is equal to the terminal PD plus lost volt or lost voltage, whatever you say, according to Kirchhoff's second law, which is based on the principle of conservation of energy, you know. So the EMF is equal to terminal potential difference plus the lost volt. And here the bulb represents the external resistance, and the internal resistance always is denoted by small r. So battery has some internal resistance. Now when the current is flowing, this current flows through the external and internal resistance, both. So this EMF, which is terminal potential difference plus lost volt, we can split the terminal potential difference into I times R, where big R represents the resistance of the bulb in this example, and I times small r, where small r represents the internal resistance usually. So VL is lost volt, as I said, and if I take I common, so this is the expression as you see, and subjecting I, it is EMF over the external resistance plus internal resistance. This is the expression of current. All right. It is to keep in mind that this big R represents the total external resistance. In this example, the external resistance is just the resistance of the bulb. But if the case is that there are a number of components externally connected with the battery, each of them has some particular resistance, then the terminal potential difference would be I times the total resistance externally connected in the circuit. Okay. Now look at how this equation, this EMF equals to terminal PD plus lost volt, as we said, this equation is true according to Kirchhoff's second law. How we can prove it that this equation follows conservation law of energy. So we are going to get an equation that power delivered by the battery is equal to power dissipated by the external resistance and power dissipated by the internal resistance. So power means the rate of energy transferred. So how much energy has been transferred per unit time by the battery is going to be dissipated both across external and internal resistance. Now, as we know that the power formula is P equals to VI. So if V is EMF of the battery, then left hand side we have EMF times I, current. And power dissipated by external resistance is I square R plus I square small r. So you see this calculation from where we get down to this equation that EMF is nothing but I times big R, which represents terminal PD, plus I times small r, which represents lost volt. And as I mentioned earlier, this terminal PD is the potential difference across the external resistors. If there is only one resistor, then I times just the resistance of that resistor. If there are a number of resistors connected in series or in whatever combination, then the total resistance will have to be considered, multiplied with the current flowing through the circuit is going to be the terminal PD. Lost volt is always I times smaller. So we have proved that this equation based on the conservation law of energy is valid. Well, moving to the next, we are going to carry out an experiment to find the EMF and internal resistance of a battery. Suppose we have been given a battery, we do not know what is its EMF, we do not know what is its internal resistance. So as I said earlier, one of the ways is I connected a voltmeter with the between the two terminals of a battery, and whatever the voltmeter reading is, I consider this to be as the EMF, because in an open circuit the current doesn't flow. So this is the case. This is how I started with, owing to the fact that voltmeter has infinite resistance, ideally, theoretically. But what if we consider practically? So infinity is not defined. Voltmeter has a very large resistance. That's why current flowing through the voltmeter is very less, effectively zero, but not absolutely zero. So we are here, therefore, going to carry out an experiment from where we can find out, we can ultimately say that experimentally proved EMF and internal resistance of the battery is this. Look at the circuit diagram. I have connected a variable resistor with the battery that has internal resistance via an emitter. I keep on varying the external resistance. And what happened? Suppose I increased the external resistance. If I increase the external resistance, then the resistance in the circuit will increase, which will decrease the current. So current goes down. This smaller current, less current, is going to flow through this internal resistance. As VL equals to I times small r, the internal resistance small r for that particular battery, when the experiment is carried on, is constant. By increasing the external resistance as current goes down, and VL is I times small r, since I goes down, VL goes down as well. As we know that Kirchhoff's second law, EMF equals to Vt plus VL. If VL goes down, Vt must rise up. Vt must increase. So here we are going to find that the terminal potential difference is increasing as the resistance is increasing. I forgot to connect a voltmeter here, so please pardon me, and do consider a voltmeter across the bulb, I mean across the variable resistor or across the two terminals of the battery. And that is something from the voltmeter we get this terminal potential difference reading. So terminal potential difference is measured from the voltmeter, current is measured from the emitter. We are going to plot a graph. So again, we are making use of this equation. We are subjecting Vt, so it is EMF minus VL, and this equation is being compared with y equals to mx plus c. Along the y-axis is Vt, along the x-axis is I. So graph is going to be a straight line having an interception on the y-axis. This interception you see, C refers to EMF and slope M refers to this internal resistance. So this is the experiment from where, if we draw the best fit line of the data being plotted in the graph, we find out what is the EMF of the battery and we find out what is the internal resistance of that particular battery. So this graphical system gives us a clear, accurate EMF and internal resistance value of that given battery. So putting this discussion a little forward, if the same identical batteries are connected in series, what will happen? The identical batteries are connected in series, so EMF is going to be doubled so is the internal resistance, as they are connected in series. So what change will there be in the graph for that new circuit where identical cell has been added to the first one and connected in series? So the change that this graph will be that interception will be double and gradient also will be double. So the graph will be started from the higher value of the y-axis and it is getting steeper. So much so that the gradient is double than before. So this is the kind of the EMF and internal resistance that we can cover up to this much. So I hope you understood it. Lots of things are to come in. Till then, thanks for watching. Do let me know if you have any question. Bye bye.